In this lecture, we'll discuss about the existence of a solution to the differential equation x dot equal to f of x, which describes a autonomous system, and we'll also see under what conditions on f will a solution not only exist but also will be unique and starts from an initial condition x0. Okay, so questions that are normally raised as far as the solutions go is, given a differential equation, whether a solution will exist or not. So when we talk of solution, we are talking of continuously differentiable solutions. So will such a solution exist or not? Is the existence of this solution over a finite interval of time, or is over a interval of time 0 to infinity? So basically, global existence of the solution. And is the solution unique? So when you start with initial condition x0, do you have one solution that is corresponding to this initial condition or and the differential equation, or do you have more than one solution? Okay, and is the uniqueness that you have is in terms of whether it is unique in the forward direction of time or whether it is unique in the backward direction of time. So whether there is a unique path that the solution will take as time progresses forward, or was there a unique path which the system took to reach a value x0. Okay, so the answer to all of these depends on the property of the function f that maps x. Okay, and this is where the Lipschitz continuity comes in. Okay, so we'll first see what Lipschitz continuity is, and then we'll see how and then we'll see whether if f is Lipschitz continuous, then what can we say about the existence and uniqueness of the solution to this differential equation describing the autonomous system. Okay, so Lipschitz continuity is essentially associated with existence and uniqueness of such differential equations. It is a condition on the functions. It is slightly stricter than what continuity suggests, but is weaker than what differentiability actually demands. Okay, so formally, if you see the definition of Lipschitz continuity, it says this. So you consider a function f which maps from a domain D to Rn, but D is again a subset of Rn. Okay. Now the function f is said to be Lipschitz at a particular point. Okay. So we define continuity at a particular point. We define differentiability of a function at a particular point. So Lipschitz continuity is also defined at a particular point. Okay. So function f is Lipschitz at a point, let's say x naught, in the domain D, if there exists two things. One, a neighborhood of x naught as defined here, is it defined by b epsilon x naught, and a finite constant L, okay, finite positive constant L, okay, such that this neighborhood and the uh, constant L that we see here together satisfy a property. What is the relationship, or what or satisfy inequality? What is the inequality? It says that if you have such a neighborhood where no matter what x and y you take from that particular set b epsilon x naught, if you take the norm of fx minus fy, so you take x from the neighborhood, evaluate what f of x is going to be, take another point y, evaluate what f of y is going to be, take a norm of it. Okay, it can be any norm that you can think of. Okay, it can be one norm, two norm, it can be infinite norm, it can be three norm, four norm, whatever it is. Now take the same norm for x minus y. Okay, so what you are seeing here is, if the distance between x and y uh, is something, then with the map x that you have, there is a distance between f of x and f of y. Okay, so if the distance between x and y is finite, and the distance between f of x and f of y is also finite, and it satisfies the relationship that the distance between f of x and f of y to the distance between x minus y will always be less than equal to the finite positive constant L. Okay, so this finite positive constant L that you see here is also known as the Lipschitz constant. Okay, so for example, suppose you take a point, take a function f of x to be equal to x squared. Okay, and you want to check whether x is so whether f of x, which is x square, is Lipschitz at x equal to 2 or not. Okay, so you just have to take a neighborhood around 2. Let's say that you choose a neighborhood to be 1 and 3. Okay, with the interval 1 and 3, so 2 is right in between. You have 1 units down and 1 units up. Okay, that's the interval. Now what you do is you take any pair of points in this interval and see whether you can find a suitable L that satisfies this. Now please note that this L is one constant that is going to be used for this entire neighborhood. Okay, if the neighborhood changes, possibly the L may change, but if the neighborhood is the same, then you should see that there is one L that actually satisfies this inequality or is able to have this inequality satisfied for the given neighborhood. Okay, so the epsilon and x naught remain constant and the L also has to be constant, it cannot change. Okay, so for example, the example that we are discussing, f of x equal to x squared, and suppose the neighborhood that we are taking around the point of interest 2 is basically the interval 1 3, and let's say that the L here is essentially, if we have take any L which is greater than equal to 6, then you can actually verify that this particular inequality will be satisfied. Okay, so if you take L to be equal to 6, then the Lipschitz constant for this function will be 6 at the point 2. If you for the interval 1 comma 3, or the neighborhood defined as 1 comma 3, sorry, 1 comma 3, yes, and if you take L to be 7, then L equal to 7 is the Lipschitz constant for the neighborhood 1 comma 3 of the point 2. Okay, so this L is not a unique Lipschitz constant that is associated with a function and the neighborhood. Okay, it's just that once you fix a L, it's the same L that should be able to satisfy this relationship for all the points. Okay, so this Lipschitz continuity again can be finely seen as the following. The definition that we see here is basically what is known as locally Lipschitz, which means that you have a domain D from which a f is mapping. Just take a point, let's say x, or let's say x naught, and you just check whether it is satisfying the inequality along with the existence of such a constant in a particular neighborhood or not, so that we can call f of x to be Lipschitz at that particular point in D. So the function is locally Lipschitz at a particular, it is just Lipschitz at a point x naught, so it is locally Lipschitz. Okay, for example, f of x equal to x square. Next comes locally Lipschitz on a set D. Okay, this was locally Lipschitz at a point, so Lipschitz at just a point. Now we come to locally Lipschitz on a set D. Now suppose you have a domain D. Okay, if the f is locally Lipschitz at each and every point that you have in the domain, okay, then the function f is said to be locally Lipschitz on the set D. Okay, now note here that the L associated at each point may be different. So L, for example, in the function f of x equal to x squared, okay, let's say that the domain is entire real axis. So we are interested, let's say, in checking whether Lipschitz at 0 or not. So when I take 0 and I take the neighborhood -1 to 1, I'll get some L. Okay, suppose that L is going to be anything greater than 1. Now suppose I want to check at 2 and I take the interval 1 comma 3, then the L will be anything greater than equal to 6. Okay, if I want to see it in the neighborhood, in the at point 4, in the neighborhood, let's say 3 comma 5, then L can be anything greater than equal to 10. Okay, and so what you observe is, with the point and the neighborhood taken around the point, there is a particular L associated with that particular point and the neighborhood. As the point and the neighborhood change, possibly the L also changes. Okay, but in this entire set, you will not be able to find one common L that will actually that can actually satisfy the Lipschitz inequality that you have. Okay, so this is why we call that this is a function which is locally Lipschitz on a set D. In this example, the D was the entire R. Okay, next comes Lipschitz on D. Now, Lipschitz on D essentially means that the function f that we have in hand is locally Lipschitz on the set D that we have. In addition to this, you will have one Lipschitz constant that can satisfy the inequality for all the points in the domain D. Okay, you will have one Lipschitz constant that will basically, you will have one finite positive constant. Let me put it like this: you will have one finite positive constant that will actually act, that can act as a Lipschitz constant for all the points in D, on over which f is Lipschitz. Okay, f is going to be Lipschitz over all the points in D because f has to be locally Lipschitz. In addition to this, there is one common positive constant, finite positive constant that you can find, which can act as a Lipschitz constant for all the points. Okay, for example, you can take f of x to be equal to x square as the example, with the domain being, let's say, 0 to 10. Okay, or exponential function e power x with the domain being 0 to 10, or sine of x with the domain being entire Rn. Okay, so in all these cases, you can actually find a one common L that will act as Lipschitz constant for all the points in the given domain. Okay, so this is what is known as Lipschitz on D. Next comes globally Lipschitz. So a function f is globally Lipschitz if f is Lipschitz on the domain of interest and the domain is nothing but the entire Rn space. Okay, example, sine of x that we just discussed. Sine of x at with d being equal to r. Okay, so x is a real number. X, so the domain is the entire real set that you have in hand. Okay, so sine of x is globally Lipschitz. Okay, so we have locally Lipschitz, which means Lipschitz at a particular point in the set. We have locally Lipschitz on the set. We have Lipschitz on the set, and then we have globally Lipschitz. Okay, now under what conditions will unique solution exist when the initial condition is x0 and the differential equation is given by x dot equal to f of x? Okay, so this is where the result comes in. So it's for, so if you have an autonomous system described by the differential equation x dot equal to f of x, and x belongs to a domain D which is a subset of Rn, f is a function that maps from D to Rn, and let's say that f is locally Lipschitz at x naught. Okay, so it is locally Lipschitz at x naught, which is again in the domain D. Now for the initial condition x of 0 being equal to this particular x naught, there will exist a unique continuously differentiable solution that will start at this initial value x naught, and this solution will exist over a finite time, over a time interval 0 to delta. Okay, so this delta can be a positive constant and it depends on the Lipschitz constant L associated with f. Now if f is such that it is globally Lipschitz, so basically f has to be a function that maps from Rn to Rn. So the domain D is the entire Rn and F is globally Lipschitz. Then for every initial condition that you can take from the Rn, the state equation x dot equal to f of x starting at the initial condition will have a unique solution that will exist for the time interval 0 to infinity. So this is known as the global existence of the solution. What you had before was the local existence and uniqueness, because the solution exists over a finite time interval. The unique solution exists over a finite time interval, and after the time interval or before the time interval, you really don't know what happens to the solution, whether the solution will exist or not, and whether the solution is going to be, if it exists, then whether it will be going to be unique or not, and so on. Okay. But if f is globally Lipschitz, then the autonomous system under consideration with x dot equal to f of x starting at any initial condition in Rn will always have a unique solution that lasts over the entire time interval. Okay, so this is a huge jump between existence of a solution over a finite time interval to the existence of a solution over the entire time interval, basically global existence. There are relaxed conditions, so you would actually encounter systems as you see things in details, uh, that the function f that describes the autonomous system may not be globally Lipschitz, yet you will find that for certain initial conditions, the solutions actually exist for the entire time interval. Okay, so um, just to throw an example for you, what you can do is just check for this x dot is equal to x squared, and check for what happens when x0 is equal to 1 and what happens when x0 is equal to minus 1, in which case the solution is going to exist for the entire time interval, and in which case the solution will exist for over only a finite time interval. Okay, when I say a solution exists is over a time interval, then essentially it means that it would not have escaped. Okay, so that is the time interval that you'd like to. Um, okay, so I think we'll stop here. Thank you.